Okay, so what's so important about the oxygen? Now the thing is it doesn't have to be an oxygen. It could be any atom that has lone pairs on it. It could be a nitrogen atom with lone pairs. It could be a sulfur with lone pairs. It could be a phosphorus with lone pairs. It can even be halogens. We're going to talk specifically about halogens. Okay, halogens go orthopara, so these are ortho-pair directors, but this halogens is deactivating, where these groups are activating groups. Okay, so what's so special about the lone pairs? Well, what do you think we got to do? We got to look at the resonance structures, at the intermediates. So your nitro is going at the ortho position right here. Okay, that's where your nitro group. Notice your nitro group is hanging off the ortho position. Okay, 4 resonance structures. Obviously, they're trying to get your attention to this one. All right, let's even do it in red. Same thing down here. Especially stable. Why is it especially stable? Well, when you have a plus charge at the tertiary position, all right, these lone pairs can actually pop down to form a pi bond there and putting the plus charge here. Okay. Now, if you go back to here, we're at the para position again. This group is an ortho para director. So same thing. These lone pairs can pop down to form the double bond there. If you look at all 4 of these structures, which one is the major resonance contributor? Okay, it's the one that I completely circled and is especially stable and yada yada yada. Okay, these are the major resonance contributors. Why? Because these carbons are not octet. That was one of the rules we learned last semester. All right, non-octet carbons are not that great. Here, everything's octet. Okay, even though I have a plus charge on the more electronegative atom, that obviously is not good, but it's way worse to not have an octet. Okay, so ortho-para positions give you 4 resonance structures. Meta attack gives you only 3, and you don't have that especially stabilized structure with the oxygen. Okay, here's the meta. Okay, so last slide, you got these resonance structures. Remember 4 of them. Remember we talked about the more resonance structures, the more stabilizing. I got 4 with the orthopara, but I only got 3 with the meta. Okay, so resonance forms show that the methoxy group cannot stabilize the sigma complex in the meta substitution. Okay, so that is why anisole type of groups, or if you have some sort of lone pair group adjacent to here, you can form that resonance structure, stabilizing the ortho-para sigma complexes. All right, this is a reaction just to show you if you had 3 equivalents of bromine, you can brominate at the spots. Since these are so much more activating, since these oxygen groups are so activating, you don't even need a catalyst. Notice I don't have a catalyst here. Notice I don't have iron tribromide. I just have bromine. Okay, notice no iron tribromide. All right, well Steve, I thought you just said for aromatic reactions you need catalysts. Well, yeah, you do for most of them, for benzene, but this is such an activating group. Remember last slide it said it was 10,000 times more activating. Do you think you need a catalyst with something that activates this ring so much? Obviously the answer is no. Okay, so you don't even need a catalyst. You can just take these types of compounds, anything that has lone pairs on it, and just throw in your electrophile, and you can completely halogenate or do anything you want to the aromatic ring. So the methoxy group is so strongly activating the anisole is quickly tribromated without a catalyst. Here's the amino group. We already talked about this. It doesn't matter if it's oxygen, nitrogen, sulfur, phosphorus, same exact thing. All right, and actually anilines are more reactive than oxygens because they are less electronegative. So there you go. It's even more reactive. Okay, here's a summary of the activating groups. All right, notice the groups all have lone pairs. Lone pair, lone pair, lone pair, lone pair. I just have oxygens and nitrogens, but you can do sulfurs and phosphorus. And you have alkyl groups. Now this is sp3. Make sure it's sp3 hybridized. Okay, those are your activating groups. All right. Now, what makes a deactivating group? It's something that's electronegative or electron withdrawing. All right. So if the substituent in the ring is electron donating, the ortho pair positions are activated. If the group is withdrawing, then it's deactivating. So what's examples of withdrawing? Nitro group is a withdrawing group. Okay. However, it's so withdrawing that it actually now favors the meta positions. Notice you don't really have much ortho and like virtually zero para. Okay, so electron withdrawing groups. But not only that, I'm going to kind of show you a trick. Okay, so last slide we learned, let me kind of summarize this again for you. In order to be an ortho para director, I'm going to tell you the secret so you don't have to memorize groups. If the group adjacent to the aromatic ring has a lone pair on it, or is an sp3 carbon. Those are the two criteria you need to be orthopara. That's it. Okay, so you need to look at the Lewis structures of the compounds directly adjacent to your aromatic ring. If you have these two criteria, you got an orthopara director. Okay. If your group that's directly attached to your aromatic ring has a pi bond attached to it, so the pi bond has to be adjacent to the aromatic ring, it is a meta-director. Notice nitro. What's the Lewis structure for nitro group? All right, I'll draw it here. Nitro has a double bond oxygen, and then your aromatic ring. Notice there is no lone pair on this nitrogen. It actually has a plus charge, plus a negative charge on your oxygen. There is no lone pair on this nitrogen. So because of the pi bond, also you'll see because of the plus charge, it deactivates it and it actually stabilizes the meta carbocation. And we're going to see in a second. All right, so electrophilic substitution reaction nitrobenzene are 100,000 times slower than the benzene. Exact opposite. The product mix contains mostly the meta isomer and only small amounts of orthopara. Okay, so let's see why. Okay. If it attacks the ortho position or the para position, you're going to get this tertiary plus charge. But this is saying, in the last case we saw it was especially stable. But this case, what do we see? It's especially unstable. Why do you think it's unstable? Okay, well, it's kind of telling you. You got two positive charges next to each other. Do you think that is stable, or do you think that is incredibly unstable? That's incredibly unstable. You do not want two plus charges next to each other. This is horribly bad. Okay? Well, in the para position, the same thing happens. Okay? So the nitro group is strongly is a deactivating group when considering its resonance forms. The nitrogen always has a formal positive charge. Ortho-para addition will create an especially unstable intermediate. Okay? In the meta position, you don't have that. You have your plus charges at all the carbons. Okay? So for meta substitutions, you can think of it, it's not that any one of these is more stabilizing, it's that one of these is not so unstable. It's like the exact opposite of why orthoparas work. Okay? The meta positions don't put positive charges near each other. So here's activation energies compared to benzene. Meta is still higher in energy, but it's not way as high in energy as the orthoparas. Okay, so deactivators and meta-directors. Most electron withdrawing groups are deactivators and they're meta-directors. All right, the atom attached to the aromatic ring has a positive or partial positive charge. Also, it'll be a pi bond as well. All right, so let's also put here or pi bond. All right, electron density is withdrawn inductively along the sigma bond, so the ring has less electron density than benzene, and thus it will be slower. Okay. Notice here's a pi bond. Okay. Now there's a pi bond here giving a partial positive on this carbon. So if you have an orthopara attack and you have a positive at the tertiary, now you have a partial positive to a positive. Very bad with orthopara. This would be for orthopara. Meta, you do not have this. So that's why something with a pi bond, carbonyl, would be a meta-director. Okay, the ortho and para substitution of acetophenone when the carbon atoms bearing the positive charge is the carbon attached to the positively charged carbonyl carbon. Since like charges repel, this close proximity of the two positive charges is especially unstable. All right, so you're going to want to do a meta attack. So this shows you in the meta position. Notice your positives are here, here, and here. Okay, you do not have a plus charge here, which is where you do not want it. Here are other deactivating groups. You're going to notice they all have a pi bond. Pi bond, pi bond, pi bond, pi bond, pi bond. All right. Also, carboxylic acid. I don't have a carboxylic acid here, but imagine I had a hydrogen here. That's a pi bond. An ester. I'm sorry, I have an ester. An anhydride, pi bond. Quaternary nitrogens because of the positive charge. All right. These are meta-directors. So what about halogens? What's the story with halogens? I told you halogens were orthoparas. Okay, they have lone pairs, but they're one of the only orthoparas that's deactivating. Okay, they are an orthopara-director that's deactivating. All other orthoparas are activating. So why are these deactivating? Well, you have the lone pair to kind of stabilize the plus charge, but chlorine's electron withdrawing. Remember, to be deactivating, it's got to pump electrons in. Halogens pump electrons out. So you still get mostly orthopara. You might be thinking, well, why is it more para? I just have a little chlorine. Well, chlorine is probably like about that big compared to the aromatic ring. Okay, chlorine's a pretty big atom. Okay, so because of the electron withdrawing, the inductive effect going the opposite way, it makes it a deactivating group. Okay, but you still get this stabilizing structure. Okay, whether the ortho attack, the para attack, the meta attack, you don't get it. So that's why halogens are not meta-directors. Okay, and again, here's an energy diagram. You can look at these on your own. So here's a good summary. I like this summary. Okay, activating groups, things with lone pairs. I'll put LP, lone pairs. Your alkyl group, your sp3 hybridized. We didn't talk about this, but actually an aromatic ring attached to another aromatic ring makes it orthopara-director. We're not going to talk about why, but it does. Okay. Halogens, remember halogens have lone pairs on them, so they are still orthopara-directors, but they are now starting to become deactivating because of their electronegativity. And now you've got all of the pi bonds. Everything here has a pi bond that has a plus charge. But remember, these all have partial positive charges. Partial positive, partial positive, partial positive, partial positive. That has a full positive. That's a positive. Because of these positives, okay, they don't want that positive charge next to it. Notice these are all partial negatives. We didn't really talk about this, but now if you think about it, even these are all partial negatives compared to the carbons attached to. So now we'll have a we'll have something that has a partial negative charge adjacent to your plus charge. That's good. Okay, but in the meta case, you'll have positive charges next door to something that has a partial positive. That's bad. Okay, so there you go. That's a pretty good summary of how you can determine if it's an orthopara-director or if it's a meta-director. Okay, remember which substituents are activating and which are deactivating. Okay, activators are orthopara-directors with the exception of halogens, and deactivators are meta-directing except for halogens. So I just said that. Okay.